Hello again. This is Professor Vijay Chalavendra from the Department of Mechanical Engineering, University of Massachusetts, Dartmouth. This is the third presentation as a part of series of presentations I have been making on multifunctional natural fiber composites. This project is sponsored by National Science Foundation of United States of America. The motivation for the project as well as the fabrication of the composites is not discussed in this presentation. I request the viewers to look into the link provided underneath here for the more details. In this study of mode 1 fracture experimentation, to measure the electrical response, we employed a double cantilever beam sample as shown in this picture, where this is a standard sample people have been using for the composites, where the dimensions of the sample are provided in the image. The important part of this study is to develop a novel 4 circumferential probe measurement system. This is not available in any standards. We have to think about a better way to send the current as well as to measure the voltage when the crack is propagating. Hence, we employed to send the current through the thickness of the sample as shown in this picture and measure the voltage along the thickness just above and below the crack as shown in the picture. In this study, we have a simple experimental design where we wanted to understand the electrical fracture response with 2 different carbon fiber lengths of 150 microns and 350 microns with the flock density of 4 different fiber densities where we have 500, 1000, 1500, 2000 in increments of 500s, and we wanted to go with only one jute orientation for the fracture studies, which is uniaxial fiber orientation. In this study, we have 2 different weight fractions of carbon nanotubes, one for 350 microns, which is 0.1%, and 0.5% for the 150 microns carbon fiber composites. The reason we wanted to use 2 different things because 350 micron system provides a better conductive network compared to 150 system, as we saw in the previous presentations. Coming to results, as you can see here, with the no flocking conditions, the fracture initiation toughness is around 1.5 kilojoules per millimeter square. However, by addition of the carbon nanotubes, by addition of the carbon fibers, where you can see a significant improvement in the fracture initiation toughness. For a system of 2000 flock density of 350 microns carbon fiber length, we see a 75% improvement in the fracture toughness value, which is a significant improvement where we wanted to see these multifunctional effects of adding these carbon fibers into the system. Now, coming to electrofracture response here, this slide has 4 different pictures where we are interested only to talk about in this presentation 350 microns carbon fiber length, where we have 4 different flock lengths, 500, 1000, 1500 and 2000. As you can see, for 500 there is a lot of noise in the electrical response because there is no significant electrical network in the system. With the small flock density of 500, you don't have enough carbon fibers between the laminates. Hence, you are not breaking a conductive network within the whole plane of the crack propagation. Hence, you see a maximum percentage of around less than 10% of electrical resistance in the system of 500 fibers per millimeter square. However, if the flock density is increased to 1000 fibers per millimeter square, you see a gradual increase in resistance and there is very less noise too. But if you look at the maximum value, is around 40% of change in resistance, which is expected because the electrical network is much better compared to 500 fibers per millimeter square. As you increase the flock density to 1500, you can see that the maximum resistance change as the crack is propagating along the system is around 60%, is much improved than 1000%. However, if you see 2000 fibers per millimeter square, it is actually much higher, which is 400%, because as the crack is propagating, you are breaking the network perfectly between the 2 interfaces. That's why you see a very high resistance change. Moreover, the initial resistance of the systems decreases as the flock density increases. Hence, you see the maximum resistance at which they break is also increasing. And one additional thing we want to see here is for 2000 fibers per millimeter square system, you see a corresponding increase in resistance for each drop in load value. That's a very unique thing you can observe in 2000 fibers per millimeter square system compared to any other system. Here, I wanted to talk about the effect of carbon fiber length. We took a system of 2000 fibers per millimeter square as a reference to compare these two systems, where you can see the crack initiation point happens at the same location of 5 millimeter displacement for both cases. You do not see a significant change in resistance before the crack initiation point. However, you start seeing some kind of linear response of the resistance change in both systems in the zone 2. The interesting part of the resistance response is in the zone 3 for both systems. As you can see in 150 microns system, there is a increase in electrical response, but you don't see corresponding drop for each corresponding drop in load. There is no corresponding increase in resistance. It's kind of gradually changing because the network is not as good as 350 microns. However, if you see for a system of 350 microns, those green lines are shown there to give you information about how resistance is increasing for each drop in load, where there is a stick-slip mechanism is happening in the system because of the bridging of the carbon fibers between the two laminates. So we wanted to achieve crack bridging, at the same time need to get a sensitive electrical response from the system. Hence, it seems like 2000 fibers per millimeter square system with 350 microns carbon fiber length system provides both very high improvement in fracture toughness of 75%, at the same time is providing us a sensitive electrical response as you see in this picture. So to conclude this study, the carbon fibers addition between the jute fabrics enhance the fracture toughness by 75% for a system of 350 micron length and 2000 fibers plaque density compared to non-plaque condition. And also with increasing plaque density, the direction of the crack propagation is more stable and fewer fluctuations with less noise. And composites of 350 micron length and 200 fibers per millimeter square plaque density provided a sensible network compared to all other composite systems on damage monitoring during the crack propagation. Hence, we recommend using that system in the real life applications. And I've only talked about 350 micron length for different plaque length densities. If any viewer is interested to know more about these results, I request them to look into this publication published in Journal of Natural Fibers for more details. Thank you very much.